Today we're picking up where we left off before exam 2, talking about the unit cells of our three crystals of pure elemental metals. Simple cubic, body-centered cubic, also called BCC, and face-centered cubic, also called FCC. So prior to exam 2, we introduced the concept of the unit cell, and we talked about the unit cell as the smallest representative piece of a crystal. From the unit cell, you can determine all the truly relevant properties of a crystal, including chemical formula, density of the material, and several other important physical properties. What we want to do today is talk more about the structure of the unit cell and how we can use the picture of the unit cell to determine some fundamental aspects of our pure metals, like number of atoms in the unit cell, atomic radius of the metal's atoms, and density of the metals specifically. So if it's been a little while since you went back and looked at our introductory remarks on unit cells from last Wednesday, I'd encourage you to go back and check out that last lecture and then come back into this one. We're zeroing in on unit cells and crystals in general, as I said in our last little mini lecture about X-ray diffraction, because by understanding where atoms are in a crystal, we have been able to really advance our understanding of how molecules interact with one another, design better drugs, better therapeutics, and has given the field of medicine in particular a quantum leap forward to be able to actually see where atoms are in a molecule. And in modern chemistry, XRD analysis of specific chemical compounds to determine their structure has been supplemented and in some ways surpassed by other faster techniques and a little more user-friendly techniques like nuclear magnetic resonance spectroscopy or NMR. But XRD is still kind of the primary instrumental tool to determine the absolute structure of, say, the proteins on the coat of a virus, the structure of biomacromolecules like DNA. And so understanding something relatively simple like how the unit cell of a metal can be interpreted to understand things about the metal gives you kind of a good window into what crystallographers do and how they can expand this same type of logic to examine more complicated unit cells like those of ionic compounds and molecular solids like biomacromolecules, crystallized DNA, sucrose, starches, etc. All right, so how the unit cell fits in. The first way in which a unit cell is the smallest represented slice of a crystal is, remember that we don't define the unit cell with atoms included. Instead, the unit cell is a box that often includes parts of atoms in the corners of it or atoms in the face. If you take that unit cell and stack unit cells top, bottom, sides, etc., and build out more unit cells around the original unit cell, you can reconstruct the entire crystal. So the unit cell is just the smallest representative piece that stands for the whole crystal. You can think of the unit cell almost like a building block or a Lego, that if you just stacked more of the same Lego on top of it in 3 dimensions all around the original Lego, you would reproduce a larger version of that original unit cell, and the unit cell actually contains all the fundamentally important information that you need to rebuild an entire Lego structure from a single Lego. So it's by stacking the unit cells in all dimensions that we can recreate the entire crystal. We refer to these edges of the unit cells as lattice points. So the lattice points refer to the 8 corners of a cubic unit cell. And remember, in all of our metal unit cells, we have an eighth of an atom included in the unit cell at every corner. In your actual crystal, those are 8 atoms sitting in close proximity to one another, and a small slice of each of these corner atoms is included in the unit cell. And again, if we were just to stack unit cells out in all directions, these spheres, which represent the atoms of the crystal and the whole rest of the crystal, will be able to reconstruct itself. So a unit cell is really more thinking about a crystal from a crystallographer's perspective, and the dimensions of the unit cell are fundamentally related to the types of information that you get from X-ray diffraction experiments. So they're really a crystallographer's way of thinking about a crystal as opposed to thinking about a crystal from an atom's point of view. However, if we know the unit cell's dimensions and basic structure, we can get some very important information from the unit cell itself that can be immediately traced back to observable properties of the material. For instance, the edge length of a cubic unit cell can be directly related to the atomic radius. So I'll show you how to do that. XRD is therefore one of the fundamental ways to measure the radius of an atom. And the number of atoms per unit cell in conjunction with the dimensions of the unit cell can be used to find the density using simple dimensional analysis. We'll also show you an example of how to do that today, and we'll have more practice for you on that topic tomorrow. Lastly, we can also talk about the position of an atom in a unit cell or in a crystal in terms of coordination number. Coordination number refers to how many nearest neighbor atoms a specific atom has in a crystal. So for instance, if we're talking coordination number, we may step outside the unit cell and think about the crystal again from an atom's perspective and say in a simple cubic unit cell where each unit cell is only defined by the 8 atoms at the corners, how many nearest neighbor atoms does each atom actually have? So if I'm interested in this polonium atom, remember polonium, capital P little o, is the only metal that crystallizes in a simple cubic unit cell of all the metal elements on the periodic table. A polonium atom would have 6 nearest neighbors in a simple cubic unit cell, here, here, here. So its 6 nearest neighbors are arranged in an octahedral geometry arrangement around it. And we can get this by looking at the unit cell or stacking unit cells on top of each other. So in your simple cubic unit cell, the coordination number of any atom in the simple cubic cell is 6. Fundamentally, we talked last time about how as the unit cell gets more complex, body-centered cubic is more complex than simple cubic. FCC is more complex still than body-centered cubic. These geometries get more complex, and as a result, actually more of the unit cell is filled with atoms rather than empty space. And as a result, in an FCC unit cell, you have 4 atoms, or the equivalent of 4 atoms contained within the unit cell. In a body-centered cubic unit cell, you have 2, and in a simple cubic unit cell, you have 1. Based on how we observe a unit cell to look and how the unit cell is defined by its crystal lattice points, the atoms at the corners, we can also make simple trigonometry arguments that allow us to relate the dimensions of the unit cell to the atomic radius of the metal atoms that make it up. And so for each of our 3 unit cells, there's a straightforward formula that defines the relationship between the edge length of the cube, which we call lowercase l. So lowercase l is how far across the unit cell actually is, how wide the unit cell actually is. And then r is the atomic radius. So for a primitive cubic unit cell, 2 times the atomic radius is equal to the edge length. We'll show you how we derive that. In a body-centered cubic unit cell, which is the hardest one to visualize, 4 times the atomic radius is equal to the edge length L times the square root of 3. And in a face-centered cubic unit cell, we can show you using Pythagoras' theorem that 4 times the atomic radius R is equal to the edge length times the square root of 2. How do we come up with these formulas? Well, we can come up with a straightforward mathematical relationship between the edge length of the unit cell and the atomic radius just by looking at the unit cell itself. So for instance, our simple cubic lattice cell, we have an atom that defines each corner of the cell. 1/8 of the atom is inside the unit cell, and the center of each atom is at the lattice point at the edge of the unit cell. And so as a result, what that means is if we look at each edge length, we have a distance half an atom in and a distance half an atom in. Those 2 atoms are touching. Therefore, your edge length is 2 times the atomic radius, or 2r. In a body-centered cubic unit cell, the relationship is a little harder to see, but in a face-centered cubic unit cell, which I'm showing here on the right, you can look at the face-centered cubic unit cell's face as 2 right triangles forming a square. Because the cubic unit cells are squares, we can define a right triangle in any side of the FCC unit cell, and we can say, okay, unfortunately in an FCC unit cell, the corner atoms do not touch one another because we have another atom intercalated in the center space of the face right here. But we can still define the edge length L. Here's the edge length L. Here's the edge length L. Okay, so we have L and L. And if we look across the diagonal of the face-centered cubic unit cell, we have 4 times the atomic radius because we have the corner atom touching the atom in the face and then touching the other corner atom. So that's 1 atomic radius. The diameter of an atom is 2 times the atomic radius. There's another atomic radius. So the hypotenuse of our right triangle is 4r. Using Pythagoras' theorem, a squared plus b squared equals c squared, we can say that the edge length squared, L squared, plus the edge length squared, L squared, is equal to the square of the hypotenuse, 4r squared, which would be 16r squared. If we simplify that formula and rearrange to solve for r, we'd see that the atomic radius is equal to the edge length times the square root of 2 divided by 4. And so we can still calculate the atomic radius. Where we get this formula for the body-centered cubic unit cell is rather hard to see in a two-dimensional representation, but it involves a similar type of Pythagorean theorem argument, except in the body-centered cubic unit cell, you actually have to draw your hypotenuse through the diagonal that goes through the middle of the unit cell rather than a face to build up a valid relationship that's easy to solve between atomic radius and the edge length of the cell. But what these formulas mean is, if you only know 2 things, into which cubic unit cell geometry your metal packs, and the edge length of the crystal cell, unit cell, which you can get from XRD, you can calculate the atomic radius of the metal very simply. And so XRD is one of the primary tools that was originally used to establish the atomic radius of the metal elements.